Okay, I thought I would start just by briefly going over the problem that I said to you last week on the potassium hydrogen against silica diagram. The first part of the problem involved simply balancing the weathering reactions for K feldspar and K feldspar reacting with hydrogen ion to make muscovite, and muscovite reacting with hydrogen ion to make kaolinite. So the secret here, and which I mentioned last time, is that we balance by assuming that the aluminiums remain in the solid state, so that there's no aluminium in solution. And I'll show you a justification for that assumption later. Anyway, so we need to balance the aluminiums. We have 3 in muscovite, so we need 3 K feldspars. We have 1 potassium, so that means we are releasing 2 potassiums. And to balance the charges, we need 2 hydrogens on this side. So we balance the charges by releasing the potassiums, balance them with hydrogen ions, and then we need to figure out how much water we need. Because this is all happening in aqueous solution, there's lots of water, so we can add or subtract as much water as we like. So we have on this side, we have 9 silicons. And here we only have 3, so obviously we need 6 H4SiO4s. Okay, so that means that we need 24, 34, 36 oxygens. And we've only got 24 here. So we need 12 H2Os. And then we check to make sure that works, we check the number of hydrogens. So on this side we've got 24 and 2 is 26. And here we've got 2 and 24 is 26. So this is a balanced reaction, balanced charges, balanced masses. And you can do the same thing with our muscovite to kaolinite reaction, which I've done there. You'll notice there's no silica released in this reaction. That's quite important. No silica is released. We have 6 silicons here and 6 there. All right. Now I gave you I gave you for the reaction not that reaction, 2H plus feldspar plus 9 H2O equals kaolinite. So I gave you the feldspar kaolinite reaction. Which produces 4 silicas. Okay, and for that one I gave you delta G0 equals 41,000 plus 41,450 joules. And delta G0, so 4150 over 2.303 RT, 298, is equal to minus the log of the equilibrium constant. So we're going to take, we'll assume that the activity of that is 1, and the activity of that is 1, and the activity of water is 1. So the equilibrium constant then is simply going to be K plus squared in concentration times H4SiO4 to the 4th over H plus squared. Okay, so all the activities here, so we'd have the activity of this one in the numerator, which is 1, and the activity of that and that in the denominator, and that's also 1. So I've just left them out to start with. And so that comes to be equal to minus 7.26. Alright, so this is minus 7.26. And then we separate, did this last time, so plus, that's plus 7.26, so the log k is minus 7.26. If we take out the 2 outside and separate the silica from the k plus and the h plus, we get, and change signs, we get 2 log k plus over h plus plus 4 log H4SiO4 equals minus 7.26, or log k plus over h plus plus 2 log H4SiO4 is minus 3.63. Okay, did that last time. So I showed you how to plot that on a diagram of k plus over h plus. Where shall I put this diagram? Let's put it here, I think. Log k plus over h plus against log H4SiO4. So it's a concentration diagram, log concentration. And I seem to remember we had numbers like plus 12 and plus 4 and minus 8 and minus 4. Remember that this silica in solution is also very low in general before a quartz or amorphous silica starts to precipitate. Okay, so we've put in k plus over h plus. Oh, we put in minus 8. So 2 times minus 8 is minus 16. Put it on that side. It's 12.37. That's silica minus 8. And if silica is minus 4, it's 8. It's 4.37. So good there. And attempt to draw that a straight line. Well, I went fairly close. Put it there. So that's the line, and I told you how using Le Chatelier's principle, if we pump up the potassium content, we drive towards feldspar. We pump up the hydrogen concentration, we drive towards kaolinite. So the feldspar is stable on the high side, and the kaolinite is stable on the low side of that line, low k plus over h plus, or high h plus if you prefer. So then, for this reaction, here, I gave you log k equals minus 4.32. minus 14.32, yeah. And that corresponds now to log, and let's make the same assumptions as before, that this is in its standard state, activity 1, this is activity 1, and this is activity 1, so it's just k plus squared over h plus squared times H4 SiO4 to the 6th. That's squared. Separate them. So it's log, it's 2 log K plus over H plus plus 6 log H4 SiO4 concentration equals minus 14.32. Divide 2 log K plus over H plus plus 3 log H4 SiO4. Start to fade away here. Is minus 7.16. Okay, so let's, this is for this reaction. So let's do the same again. Let's put in minus 8 for silica. So 3 times minus 8 is minus 24. Put it on that side and we get 16.84. So it's up there somewhere. Continue my scale. And if we put in minus 4, it's 3 fours are 12, so this will then become 4.84. So it's it's just above this one. Okay, 4.84 on this K plus over H plus. So we draw a line there. I'll just remove this for a second. And it's, obviously the slope is steeper because there are three log silica. Oh God, could do with a ruler here. Okay, and they fairly obviously cross, which is kind of interesting. And we use Le Chatelier's principle again, and that says that if we pump in potassium, we go to feldspar. If we pump in acid, we go to muscovite. So the high potassium side is feldspar. So we've got feldspar there, and we've got feldspar there. Right, okay. So we've got those crossing, and now we need to do something about the third reaction. And that's this one. I'll just rub this working out here so as we can put them all more or less on the same diagram. Okay, so So log K for this one is minus 7.26. And log K for that one is minus 14.32. And we need to get this one. Now this one doesn't involve any silica, so we have to eliminate silica. And the way we can do that is multiply that one by 2, multiply that one by 3, and subtract this one from that one. Okay? So if we take two of these, we multiply that one by 2, that's 6 of those, and multiply that one by 3 is 6 of those. Okay, so we can eliminate feldspar by taking 2 times the first reaction and subtracting 3 times this reaction. Alright, and we can do the same with log K, because log K's are additive, can be added and subtracted in the same way as free energies, enthalpies, and so on. So we can eliminate feldspar by taking 2 of that one. So that's 6 feldspar plus 6H plus 24 H2O equals 2 muscovite plus 4K plus 12 H4 SiO4. And this one will be, when we multiply by 3, is going to be, sorry, this one, multiply this one by 3, is 6 feldspar. Try another one. Plus 6H plus 27 H2O sorry. Three, 6. That should be 4H plus, sorry. (27 H2O) is equal to kaolinite, 3 kaolinites plus 6K plus 12 H4 SiO4. So we subtract, or we can do it either way around. Let's subtract this one from that one, and we'll get 2H plus plus 3H2O equals 6 kaolinite Okay, that's equal to 3 kaolinite minus 2 muscovite plus 2K plus, and the silicas disappear. So just rearranging that, we have 2 muscovite plus 2H plus 3H2O, let's try to make sure I get the right answer, is equal to 3 kaolinite plus 2K plus. And log K for that reaction is going to equal 3 times this one, which is minus 7.26, minus 2 times that one, minus 2 times 14.32. So that comes to 3 times minus 7.26. Obviously that's minus 14.32. Minus 2 times minus 14.32. Which equals 6.86. Okay, so and that equals, so this one then, log K for this one is plus 6.86. So 6.86, again, if we assume all activities are 1, that's 1, and that's 1, except for the hydrogen, that's 1, except for hydrogen and potassium. 6.86 is log K plus squared over H plus squared. Take the 2 outside and take it across. So log K plus over H plus over H plus is 3.43. All right. So that's log K plus over H plus is 3.43. There's no silica in the reaction, so it's independent of silica. So that's a horizontal line at 3.43, and it should go through the same point as the intersection of the other 2 lines, like so. And again, we use Le Chatelier's principle. High potassium, pumping up potassium, will put us on the muscovite side. So high K over H is muscovite. So that's muscovite, that's kaolinite. Now we find we're in the same situation as we were with the aluminosilicate phase diagram, is that we have lines which cross and we need to figure out which parts are stable and which parts are metastable. That's fairly easy to do again, as it was in the previous occasion. Remembering, this is at fixed temperature and pressure, so this is at 1 bar and 298 degrees K. And what we can see is that feldspar breaks down to muscovite everywhere to the left of that line. All right? And kaolinite breaks down to muscovite everywhere above that line. So this feldspar kaolinite line up here cannot be stable. So this is metastable. Like so. All right? So muscovite and kaolinite are unstable with respect to feldspar everywhere over here. So that part of that line has to be metastable. And muscovite is unstable relative to feldspar everywhere over here. Everywhere over here. So this part of that line, wrong way around. This part of this line has to be metastable here. Okay? Because muscovite isn't stable anywhere below that line, below the muscovite kaolinite line. So the muscovite feldspar line has to be metastable down here. So the final diagram, if I put the stable parts in heavy, looks like so. So this is the field of feldspar, this is the field of muscovite, and this is the field of kaolinite. Okay, that's the feldspar kaolinite line. Okay, so I hope that's fairly obvious. Right, kaolinite is stable here, feldspar is stable over here, so this part of that line is stable. Alright, now I mentioned that I asked you to balance all these reactions with aluminium in solid phases, because I said that aluminium was the most insoluble of the elements, major elements that we're concerned with. And I'll just give you a quick demonstration of that. Now, the most aluminium-rich phase that we find in nature is gibbsite. Aluminium, well, actually that's not quite true, but in soils at low temperature, it's gibbsite, aluminium hydroxide. Now, it's not completely insoluble. It can dissolve to a tiny extent, and I mentioned that there are numerous different aluminium complexes in solution. So if we react aluminium hydroxide with acid, then one species that we can get in solution is AlH2+, and log K for that reaction is minus 1.2. Okay, so we ask ourselves, how much of this species is in solution at pH 6? A nice, fairly straightforward sort of neutral-ish pH. And log K minus 1.2, so log K equals minus 1.2, and that equals log AlOH2 over H plus, and then we'll have the activity of H2O and the activity of AlOH3 in gibbsite. We'll set these to 1, so water's pure and our gibbsite is pure. So minus 1.2, so let's set those to 1 and we separate out the hydrogen. So that will be log AlOH2 plus minus log H plus. So that there is pH. Plus pH. So at pH 6, we put 6 on the other side. At pH 6, minus 7.2 is equal to log the concentration of aluminium hydroxide. Or the concentration is 10 to the minus 7.2 molar. Not very much, okay, in a technical term. Well, let's think about some other possibilities. There are other species. We can look at this one. Gibbsite plus 2 hydrogens. And that makes AlOH2. Sorry, AlOH2 plus 2H2O. Log K for that one is plus 3.04. So maybe that's going to work out better for us. Now log K is going to equal, again we'll assume that's activity 1, that's activity 1. So that's going to be log of concentration of AlOH2 plus over H plus squared that's equal to log concentration of AlOH2 plus minus 2 log H plus, so that's plus 3.04. And so if we make that, that's 2 pH, so pH is 6, so that's 12, minus 12 on the other side, it's going to be minus 8.96. Okay, so that's even less than this in this case. All right, I mentioned Al3 plus as a species. That turns out to be even less concentrated in solution. But we can look at the one with the highest number of OHs in it. So AlOH3 Gibbsite plus dissolves to the AlOH30, and log K for that one is minus 7.01. There's no hydrogen ions involved in this reaction, this solution reaction. Therefore, this reaction doesn't depend on pH. We always have the same amount of aluminium OH30 in solution. So log AlOH30 is equal to minus 7.01. Again, 10 to the minus 7.01 molar. Maybe we should do aluminium 3 plus just for completeness. So we have that for the AlOH3. We have that for AlOH2 1 plus. And we have that for AlOH2 plus. Sorry. That. So 10 to the minus 8.96 molar. For Al3 plus, the reaction AlOH3 solid gibbsite plus 3H plus equals Al3 plus 3H2O log K is plus 8.05. We'll assume again activity 1 for water, so 8.05 is going to equal log concentration of Al3 plus minus 3 log H plus, and that of course is 3 pH. pH 6, that's 18, so that's going to be minus 9.95. Is that right? Yeah. Or Al3 plus is 10 to the minus 9.95 molar. So as I said, aluminium is pretty insoluble. By far the dominant one, you can add them all up and you just get a number that's very close to that. 10 to the minus 7 molar is the approximate maximum concentration with the most aluminous mineral we could think of, which is gibbsite. Okay, the last topic that we're going to cover in the course are oxidation reduction reactions. Very important in the Earth. If we look, the element we know most about in terms of oxidation and reduction is iron. And if we look at the Earth, in the core, as we know, is metal, so that's iron of oxidation state 0. And we know at the surface, if you leave some metallic iron out to in the weather, or in the old days, cars used to do this because people drove them no matter how rusty they were. But at the Earth's surface, iron 3 plus, the red iron oxide, is a stable form. And in between, in the mantle, it's dominantly Fe2 plus. But with some Fe3 plus. So this might typically be 95% Fe2 plus, 5% Fe3 plus. Just off the top of my head, that's sort of a number. And one of the subject of a lot of current research is to try and figure out how, if possible, how the Earth's interior, the mantle and the core, mantle and the crust, have changed with time in terms of their oxidation state. Because obviously, very early in Earth history, the iron core segregated. So the mantle must have been more or less in equilibrium with metallic iron. Now it isn't. We can go to mantle rocks, peridotite, and we can determine what their oxygen activity or oxygen fugacity, as it's otherwise called, is based on their ferric and ferrous contents. And the way we do that in the mantle peridotite this was a research topic I spent several years on in the 1980s, and it keeps coming back. People are still very interested in it. But in mantle peridotite, we have in the regions in the upper 50 or 60 kilometers of the mantle, we have spinel peridotite. And all of this ferric iron, Fe3+, is in the spinel, more or less. And so we can write down a reaction. You know how to do this. You take the iron component of olivine, that's Fe2+, and you add oxygen, and you get the iron component of orthopyroxene, plus Fe3O4, which is in spinel. And it's not pure, this is magnetite, of course, this M member, but it's not pure, it just has 10 or 20% of this component in the spinel. The spinel is mostly magnesium, aluminium, or Fe2+, chromium. But it also has a small amount of the Fe3O4 in it. We balance that reaction. I think it has to be, pretty sure it has to be 6 of those. There'll be 6 of those. And 2 of those, I think. Yeah. So we've got 6, 12, 12. 6 silicas and 24, 18 and 8 is 26 oxygens. So that's balanced, I think. So then of course we use log K or delta G0. So log K for that reaction is obviously going to be called log activity of FeSiO3 to the 6th times the activity of Fe3O4 squared divided by the activity of Fe2SiO4 to the 6th times the activity of oxygen. So we can go to our mantle rocks and we can measure the compositions of the orthopyroxene, which is about 10% of this component. The olivine also has about 10% of that component, and the spinel, and determine how much of this ferric component. So Fe3O4 is Fe3+, sorry, it's 2 Fe3+s and 1 Fe2+, and that Fe3. So it has that in it. And we measure these and we calculate what the activity of oxygen is. And what we find, if we plot log activity of oxygen against temperature, we get curves that look like this. And this would be Fe metal, Fe2+, if we're down here, at low activity of oxygen, fairly obviously. The mantle would be here. This is Fe2 plus 3 plus equilibrium. Bigger, bigger, bigger. We get values for the mantle which is surprisingly constant, don't vary very much, within about 1 log unit in oxygen activity. This would be where Fe3O4 pure goes to Fe2O3. So that's where mixed oxidation state of Fe3O4 goes to all Fe3 plus, and the atmosphere is there, or the surface if you like. So we're talking about 8 or 10 orders of magnitude in oxygen activity between the mantle here and the surface. Another thing, if we go to lavas, we can look at Fe2 plus Fe3 plus equilibrium in lavas. This has become much more accurate in recent years because we now have micro methods of measuring iron 2 plus, iron 3 plus in very small inclusions of melt inside minerals. And these give, in general, let's say for basalts, they give values very close to the mantle values, which is kind of nice because basalts come out of the mantle, right? So we get values that within a few tenths of a log unit the same. Okay, so then I wanted to come Okay, I was going to continue and talk about what's going on at the surface, but I realise I've just about used up, I have definitely used up my time, so I'll cover that in the last lecture and present the problems that we're going to do. Okay, thanks very much.